Okay, good morning, everyone. I hope you all had a nice weekend and got some rest, and hopefully you've been outside enjoying the beautiful weather we've been having lately. Before we jump in and get started today, does anybody have any questions? Okay. If not, then just a couple announcements. First of all, I reported the projector issue to IT last week after last Wednesday's very purple lecture. They have the part on order. Apparently, they've known this has been a problem for a while. It apparently is a complicated part to get. If the projector starts becoming purple again, we will just have to deal with it. The part is on order. They will get it fixed as soon as possible. Other announcements. Remember that our first homework assignment is due 1 week from today at this point. We're largely going to finish covering the material of the first unit today. The first unit won't officially end until Wednesday, but basically what we're going to do on Wednesday is work through one big example that sort of puts everything together. We're going to finish, like I said, covering most of the material today. And then the other announcement going forward is please make sure you come to lecture on Wednesday. We will spend the first half of the lecture, if not maybe a little bit more, discussing the term paper project in quite a bit of detail. So I know some of you have emailed me with questions about that already, and I've said sort of wait for that day. That day is Wednesday. And so we will be spending quite a bit of time talking about that project in class. I think that's all I have on the announcement front. Again, does anybody have any questions before we dive in? Okay, so as you might recall, the last couple lectures, and I know it seems like they've been spaced out pretty good because of holidays and weekends and whatnot, we've been developing tools and ideas related to understanding the global positioning system in GPS technology. And so we started out by looking at what was the technology, what did it do, what was its purpose and its function, and we arrived at sort of one question that we wanted to guide our entire discussion. Who remembers what that question is? Yep. Right, so we take out our GPS receiver, we take out our phone, we turn on the GPS function, and we want to know how many satellites do we need to see to determine our location. It's a pretty straightforward question to ask, I think. What we found out then last time is that we need quite a few satellites to do it. Does anybody remember from last time how many satellites do we need? And are we triangulating or are we doing something else to determine our position? We're trilaterating, and how many satellites do we need? Okay, I hear people say 3, I hear people say 4. I'm glad there's ambiguity. Why might it be either 3 or 4?
3 includes the Earth and the exosphere.
Okay, so 3 includes the Earth as an exosphere. That's partly correct. So what we saw when we came through and we worked through all these examples last time was we were able to develop sort of this table where we could say, well, how many, it's labeled here number of signals, but think of it as the number of spheres do we have. Given the dimensionality of our problems, so are we working in 1 dimension 2D, or realistically we're working in 3D, how many spheres did we need to see? And so if we're looking at a 3D problem, what we ended up discovering last time was that we needed 4 spheres to determine our location. If all we had was 1 sphere, which is to say all we had was 1 signal, all we would know is that we're somewhere on the surface of a sphere. If we had 2 signals, we could get it down to somewhere on the circumference or on the perimeter of a circle. With the 3 signals, we could get it down to 2 particular points, and with that 4th signal, we could then get it down to a unique location. There would only be 1 point that was consistent with all 4 of the pieces of information that we had. So now, the trick now, when we're asking the question, how many signals do we need? How many satellites do we need to see? Is we need to step back and look at the problem and think about some of our assumptions. For instance, as we saw last time, how many spheres are actually pictured here in this diagram? There are 5. There are actually 4 satellites, and the 5th one being the Earth itself. Is it a valid assumption when we're talking about GPS systems that we can sort of assume whoever's using the GPS system is on the surface of the Earth? That's probably not a bad assumption. Okay, if you're an astronaut, you might need to modify things. I'm sure one of you will be there someday. But the idea then being, we can use the fact that we're on the surface of the Earth to act as one of those spheres. Again, we will treat, certainly in this class, the surface of the Earth as being a perfect sphere, even though in reality we know it's not. And so then in that sense, when we want to think about this three-dimensional problem of determining what's our x, y, z, those coordinates of our location, we needed a total of 4 spheres. And if we can use the surface of the Earth as one of them, that leaves us with needing how many satellites? 3. Okay, so a moment ago when I asked how many satellites do we need to see, some people said 3 and some people said 4. Why might we still need 4 satellites if we just said 3 is going to work? So we can account for the error in timing. So this is sort of where we ended our discussion last time, and it comes with this idea of synchronization. All of the data that we measure from the satellites depends very critically on timing. Remember, we had that speed-distance-time relation that we saw almost 2 weeks ago. And so the issue is, if we want to get very good times, we have to make sure that the clocks that we're using are perfectly synchronized and that they're, in tune with each other. In the real world, is that necessarily a good assumption? No, it's not. And so the way that we get around this is, number one, we're going to put really, really expensive, very high accuracy, very high precision clocks on which ones? The satellites or the receivers? Satellites, right. We're going to put them on the satellites because, number one, there are relatively few number of satellites, maybe on the order of 50, orbiting the Earth. And number two, if each of these clocks, as we saw, cost, I don't know, maybe $50,000 to $100,000, and the grand budget of the $12 billion it took to get that satellite system up and running, meh, who cares? That's not that much money. Versus compared to $50,000 to $100,000 in your receiver, again, as we sort of talked about last time, anyone here willing to pay $100,000 for their cell phone to have GPS functionality? I'm certainly not willing to. Okay? And so then what we can do is use a few little mathematical tricks to get around this problem and deal with this issue that the clocks may not be synchronized. So what these atomic clocks and the satellites guarantee for us is that, number one, all of the satellites are synchronized. We can think of the entire satellite system as basically having one clock. Within the error and the precision that we need for GPS, they work just fine. And so what we now have to do is deal with this offset. Is the satellite clock synchronized to our receiver's clock? And the answer, generally speaking, is going to be no, but we can use a couple tricks to get around that. And so what this all came down to, as we saw last time, was this idea of introducing a couple things. So what we have, first of all, in this lowercase ti is the actual transit time. So if we were to measure the time it took the radio signal to travel from the satellite to our receiver, so long as we measured both of those times, the time when it was sent from the satellite and the time we received it on our receiver, if we're measuring that by the same clock, so whether we're using the receiver's clock or the satellite's clocks, we've got it listed here in the notes as using the satellites, that's fine. This is the actual amount of time. And so when we do our speed-distance-time relationship, that's going to give us the actual distance that we are from the satellite, which is going to help us with that trilateration. Now the problem is, as we've been discussing, this is not the quantity that we actually measure. Because we don't know, using just our receiver, we have no idea what the satellite clock is reading at that particular moment. Instead, what we end up measuring, as I've denoted here with this big T, is this fictitious time that mixes times from the satellite's clock and our receiver's clock. And so here what we have is the arrival time, when did we receive it, based on our receiver's clock, relative to the departure time, when did the satellite actually send the signal, as measured by the satellite. So this is the actual time we measure. And we can do a little bit of algebra and introduce this other variable called tau to be basically the offset between the satellites and the receiver. So think about saying, the satellite says it sent the message at, what is it now? Let's say 8:38:00, whatever the couple milliseconds or tenths or hundredths of milliseconds time frame is for when it sent it. But our receiver is maybe off by 1 second, and it says it actually sent the signal at 8:38:002 or 02 seconds. And so there's going to be some finite offset between a time that the satellite says and the time that our clock says, even though they're both talking about the same point in time. Okay? And so what we can end up doing is, through a little bit of algebra, we can end up showing that we get this relationship now, where the actual time, that lowercase t, is just equal to the big T minus tau. Okay, now, in principle, when we're talking about GPS and finding location, are we necessarily interested in the value of tau? Do we really care what the clock offset is? Probably not. If we were engineers and we're trying to build a better system, maybe we're interested in that. Is it possible that offset could be 0? Is it possible that the clocks are just synchronized? Yeah, I wouldn't bet money on it. I certainly wouldn't bet 100 miles on it when we're thinking about location, but it's possible. Okay, so what this allows us to do then, let me erase all this off the slide, is to go and develop a different, slightly more general formulation of the problem. So what we've got on this top formula here is now this s times little ti. So that's the distance that we are from satellite I, whether it's satellite 1, satellite 2, satellite 3, satellite 4, it doesn't matter. And we can then use our three-dimensional distance formula to also calculate the distance, where now x naught and y naught and z naught are our position, and the xi, yi, and zi are the positions of the satellites. And so this is basically saying the distance that we measure from the signal is equal to the distance that we have to be from the satellite. What we can now do, though, is remembering that little ti is the actual time, we can substitute in this relation that we derived on the last slide so that we can now incorporate this big Ti, which is the variable we actually measure when we look to see GPS signals, and that offset tau. And then if we square both sides, what we end up getting is this equation down here, where now, does that time term, that this Ti, big Ti minus tau squared, does that look very fundamentally different from any of the other three terms on the right-hand side? No, not really. And so what all of this work has been able to do is allow us to account for this offset in clocks at the expense of having to add one more unknown. In the cases we were discussing earlier last time, where the only unknowns we had were our positions, so we had that x naught, y naught, and z naught, we had exactly 3 unknowns. That was a 3-dimensional problem. And how many spheres did we need to have to determine values for all 3 of those unknowns? We needed 4. So now what we've done, in this case where we can't assume the perfect clock synchronization, we've had to add one more unknown. So when we go to solve for this, we're going to have our x naught, y naught, z naught, and tau. This makes it effectively a 4-dimensional problem. And how many spheres do you think we're going to need to solve the 4-dimensional problem? We're going to need 5. And so if we assume one of those is the surface of the Earth, again, probably a good assumption, the number of satellites that we're actually going to need to see is 4. So when we ask the question, how many satellites do we need to see, depending on the clock issue, the answer is either going to be 3 or 4. If we can assume the clocks are perfectly synchronized, 3 will work just fine. If we have to deal with any sort of clock issues, we're going to need 4. But does that make sense to everyone? Okay, so again, just think about what's the number of spheres you need to determine the number of unknowns that we have. We can subtract 1 in the GPS case because we know the surface of the Earth is one of those spheres. And that gives us enough information to then solve the problem. Okay. Are there any questions on that before we move on? Okay, I just wanted to recap that because I know we went through it a little bit quickly last time, and I think it's a really neat and important point. And so then what we're going to spend the rest of the time doing today as we finish out this unit is talking a little bit about coordinate systems. So what we've seen so far, and everything we've discussed, is that to identify our location, we have an x, a y, and a z coordinate. If I were to tell you, I'm somewhere on the surface of the Earth, and my x value is 3,000, and my y value is 9,000, and my z value is 4,000, does that tell you that I'm on Long Island? And I have no idea if those numbers actually tell you you're on Long Island. I just made them up off the top of my head. Instead, how do we talk about positions and locations on the surface of the Earth? We use longitude and latitude. And so ultimately, if we're going to really think about this GPS example, what we need to do is now take those x, y, z coordinates that we were able to determine using all of these trilateration examples and somehow turn them into a latitude and longitude position, which is what people actually use to discuss their location and their position on Earth. And so that's going to be the focus of today's lecture. And so basically, sort of the question that all starts with, what is latitude? What is longitude? I know you're all familiar with these expressions, but what are they? They're certainly coordinates. Can we be maybe a little bit more specific? Yep. Okay, so they're lines or degrees that show specific positions. We're getting closer. If I had to ask you just from a fundamental geometry perspective, what are latitude and longitude? What do you think they're going to be? Are they distances? Some of you are giving me sort of funny looks. That's a good thing, because they're not distances. What else might they be? I'm sorry, can you speak up just a little bit? Okay, so they measure degrees from a certain, maybe, reference direction. And what might we call that, sort of just from a geometrical perspective? Something that's measuring degrees. It's an angle. Okay, so latitude and longitude are angles that we're going to measure with respect to some reference directions. And so looking at these a little bit more, there's a couple different types of angles that we can use when we're discussing things on spheres. And in particular, and we'll define these terms and talk about them a little bit more in the next few slides. Latitude in particular is what's called a polar angle, because it's going to measure the angle with respect to a pole. And longitude is what we're going to call an azimuthal angle. Okay? And so we've got the picture here. Let's talk about these two in maybe a little bit more detail. And so to think about longitude, as we just mentioned, it's an azimuthal angle. And what that's saying, this is a bit of a complicated definition, so let me try to annotate this on the figure here. An azimuthal angle is the angle between a direction in a plane and a reference direction that also happens to be in the plane. So what that's saying is we're going to take, when we want to think about an azimuthal angle, whatever our position is on the sphere. So maybe it's something over here, maybe it's something down here. We could be up near the North Pole, and we're going to project that position. Think about, if you're on the northern hemisphere, dropping it down into the plane that includes the equator. So think about sort of dropping that down. So maybe it's something right there. Could drop that one down to be something maybe there. And if we were in the southern hemisphere, raise it up, so that we can think about where are these points in that plane that includes the equator. And what we're now going to do within that plane is we're going to say, here's a particular direction that we're going to use as a reference. Okay, so when we're thinking about the planet Earth, what's the reference direction for longitude? What do we call that direction? Anybody know? It's not the international dateline. Yep. It's the prime meridian. So we have taken, as human civilization and culture, we have adopted the convention that our reference angle will be the prime meridian. 0 degrees. Okay? Anybody know where the prime meridian runs? How it got this famed status? It runs through Greenwich, England. Aren't they special? Okay. So there's absolutely nothing particularly special about this direction. It's just the one that we've chosen over however many centuries of human civilization to use. And so what this might be then is, suppose what we can do is make, at least in this figure, this x direction, maybe that's our reference. And so when we think about talking about longitude, what we're doing is we're measuring, if we were to take any of these points, so let's look at this one now, over here. We can start at this direction and think about drawing a line from the origin back out to that point, and we want to look at what is this angle in here. And that angle, that measure of degrees, if you want to use radians, feel so inclined, but we'll use degrees in this class for everything I say. That angle is essentially our longitude. And so you can think about then, anybody know off the top of their head what's approximately the longitude of New York City? I could be completely wrong in this. I think it's about 70 degrees west. Okay? So what that's saying is we're going to go, start from the reference direction, move 70 degrees west, and somewhere on that half line along the sphere is going to be New York. Okay, so but what that longitude is doing is it's telling us we're somewhere on sort of this half circle along the globe. Does the longitude alone give us our exact location? No, it doesn't. And so we need another coordinate, which is, of course, going to be latitude. Okay, any questions on sort of azimuthal angles or longitude before we move on? Yeah.
Can you repeat how you calculate the azimuthal angle again?
Okay, yeah, so what we're, sort of the geometric picture, so the question was, can we repeat, how do we calculate it again? We'll actually look at the equations in a moment. Sort of from the conceptual picture, what you do is take wherever you are on the globe. Let me just clear this off and we'll redraw it. You can take, suppose we're at maybe this position here on the globe, somewhere on the surface of the Earth. What you effectively do is you're going to drop that point down into that XY plane, which is, from the Earth's perspective, the plane that includes the equator. And then you're going to draw the line from the center of the Earth to that point along the plane. We'll have our reference direction, which again is maybe this positive x, and we simply just calculate the angle between those two. It seems like a lot. The equation is actually a little bit simpler, I think, but that's where it's coming from. And we'll see the equation here in a little bit. Okay, so that's longitude. Latitude, in the other sense, is our other coordinate, our other angle, and it's a polar angle. This one's maybe a little bit easier to explain. The idea that we're going to take is, now suppose we've got our North Pole directly above us. Okay? So now what we can do is locate our position on the Earth. Suppose it's here. And what we're going to do is we're going to measure the angle. If we were to start at the exact North Pole and sweep out an angle such that we're now pointing at our location, what is the angle, as I'm standing here, between my arms? Okay? That's a polar angle, because we start at the North Pole and we take the angle to whatever our point or direction would be. Okay? And so that's exactly what we can see here. We're now, here's our North Pole is usually, let me try to clear that out. Our North Pole is usually associated with the z direction. So think of it all the way up at the top of the sphere there. And if this is our point, as they're indicating in the diagram here, we can sweep out, think about sweeping from this line, tracing it down along this circular arc there. And this angle that they denote by phi, the Greek letter phi, is going to be that polar angle. Okay? So, here's maybe a bit of a trick question. When we think about now our latitude coordinates, so we saw the prime meridian was our reference direction for longitude. What's our reference direction now? What do we think is the pole when we're going to talk about latitude? Okay, here, someone say the North Pole. You had a 50-50 chance of getting it right. What's the other answer? South Pole. Okay, so how many of you have heard the joke, what's the capital of Kentucky, Lexington or Louisville? And yeah, it's Frankfurt. So here's what happened. We probably made, from a mathematical perspective, a really stupid choice for the reference direction on latitude, because what is 0 degrees latitude? It's the equator. That's not a pole. Okay, so it gets a little bit more complicated. And we'll come back and deal with this momentarily. But the idea is we're going to start at the North Pole, we're going to measure a degree, and we can do just a quick little substitution that we'll talk about later to deal with the fact that we're really using the North Pole as our reference direction. We're just calling the equator 0. I know. This is one of those places where if the cartographers had talked to the mathematicians back in the 15th century, we could have avoided a lot of headache. But such is life. So one other question to think about then, when we're talking about these different coordinates and these latitude and longitude, these polar and these azimuthal angles, what's the range of them? So what's the full range of longitude? It's the full 360 degrees. We can start at our reference direction at the prime meridian. We can rotate all the way around and come back to it. Okay? So the longitude can go over the full 360 degrees. What's the range for our latitude or for these polar angles? It's only 180, because we can start at the top, we can come down, basically hit the equator, and go all the way down to the South Pole, where now, my two hands are pointing in opposite directions. Okay, pretend they're there. What happens if I kept rotating down this way and started coming back out on what's my right? Well, then what we would do is we would end up changing this angle, and when we measure it again, it would actually be something less than 180 degrees, because we're just coming down in a different direction. And so if we were to sort of sweep through the South Pole there as we were looking at this polar angle, the polar angle remains constrained between 0 and 180 degrees, but our theta angle, or our longitude, would have changed as we sort of swept through down in the South Pole. And think about that for a moment, if you need to convince yourself of that. Okay, so what this boils down to is the more general math concept is that, as was mentioned, latitude and longitude are coordinates that we can use to identify positions on the Earth's surface. And so the question, let me get rid of some of this drawing here. There we go. So then the question, have we seen other types of coordinates as we've been discussing this GPS unit? What do you think? So we're now saying latitude and longitude are coordinates that can be used. Yep. Right, so we've seen the Cartesian coordinates because we had sort of what we were discussing last time, x, y, and z. And so these are just another way, it's another coordinate system. This is another way that we can specify our location. So let's step back and think about, what is a coordinate system? And the way that Math World had a particularly obtuse definition that I put on the slide here, it's a system for specifying points using coordinates measured in some specified way. Who thinks that sounded particularly insightful? Okay, here's what it's saying. If we're going to have a coordinate system, what happens is when we're going to communicate positions with each other, I'm going to tell you, here's some position, we have to have some consensus on a few points or a few references, such that everything is meaningful. If we're going to talk in Cartesian coordinates, so we've got these pictured here, our x, y, and z values that we've been discussing from the last few lectures, what's the common assumption? When I'm going to tell you, oh, my Cartesian coordinates are 3, 5, and negative 12, what did we have to agree upon in order for that to make any sense? Yeah, we have to agree on the location of the origin. Is there a unique spot that we could take for the position of the origin? Could I suppose right here is the origin? Yep. And so if we wanted to talk about our x, y, and z components, well, if our x is 1, well, then maybe I take 1 step forward, because that's the x direction. If y was 3, then I'm going to take 3 small steps to avoid the table, move in that direction. And of course, if z was 1, what might I do? Jump to figure out our location. Could we just as easily have said the origin is right here? Yep. In which case, okay, we're going to do y first so that I don't trip over the podium here. But then maybe I had to take, I don't know, what is it, 1, 2, I don't know, maybe about negative 4 steps in the y direction, negative 1 step in the x direction, and still my little hop in the z to reach the same coordinate. But the idea is when we're using this coordinate system, we have to agree on a couple things in the first place. And those are coordinates. When it says we're going to measure the coordinates in some specified way, that's what that's saying. We have to agree sort of what's the basis of measurement. Where's the 0 point? What's that reference? Once we have that, then we can measure the coordinates sort of in any way we choose to describe our location. And so at Cartesian coordinates, that x, y, and z, is one choice of coordinate system that we've already seen. Latitude and longitude angles belong to a different type of coordinate system called spherical coordinates, which are just another way of describing positions and locations in three-dimensional space. And so the 3 coordinates that we now get in spherical coordinate systems, you'll notice here on the figure, we have this angle phi here. Do you think that's a polar angle or an azimuthal angle? It's a polar angle. And how do we know it's polar? Yep. Right, so you can look at it, sort of this red arrow. It started up at the North Pole, and we see it just sort of tracing down and measuring out that angle. That's the polar angle. So would we associate now that phi value with latitude or longitude? It's going to be associated with latitude. Okay, likewise, we now have an angle down here, this theta. Probably by process of elimination, you can get this one. Is that going to be a polar or an azimuthal angle? It's azimuthal. And notice everything here is now being sort of swept out in this plane. Notice where this little arrow is going. From this reference direction in the positive x direction relative to that point. So that's an azimuth. And the third coordinate, so if we have a three-dimensional space, how many coordinates must we need in principle? 3. The third coordinate that we'll see in spherical coordinates, this picture calls it rho. The rest of the slides we're going to call it r. I apologize for that discrepancy. I didn't make this picture. Is basically just what's the distance from the center of the sphere. So we're going to take our origin to be wherever we want it. When we're talking about the GPS system and talking about places on the planet's surface, what are we likely going to take as the origin? The center of the Earth. You can think about the Earth as a sphere. Where does it make sense to put the center? In the center. Okay. So then, this is why when we were talking about latitude and longitude, we really only had 2 coordinates. We had just the latitude and longitude. What can we assume? If we're on the surface of the Earth, what might we assume about that distance, which would be our third coordinate in spherical coordinates? It's going to be approximately 4,000 miles. Probably somewhere between 3,950 and 3,975. But we'll just round that to 4,000 and move on with life. Okay? So for the joke, if someone asks you, if you're the center of the universe, you should say what? Are you the center of the universe? Here, no. That's depressing. I mean, that's a good answer because I'm the center of the universe. But why is that? I defined my own coordinate system. Ba-doom-tsh. Okay? So lastly, and we're not going to talk about any details of this here, but just to show you that it's possible, there are plenty of other types of coordinate systems that can be used. Typically, if anyone takes, usually these are discussed in multivariable calculus courses. The third coordinate system that you usually see in 3D is called cylindrical coordinates, which I don't picture up here because it's boring. But there are plenty of other options. You can get paraboloidal coordinates. Like I said, I don't want to discuss too much about what these are, but just to put up a pretty picture, which the projector is actually not doing a terrible job at showing. There's also a thing called toroidal coordinates, where you can think about sort of having donuts intersect with each other to determine location. And so depending on your problem and what it is you're trying to describe, there's a wide range of ways that you can discuss three-dimensional space to describe these positions and these locations. Okay? Does that make sense? All right. Anybody have any questions sort of on coordinate systems generally before we move on? Okay. So now, we might have already answered this question, but what does this all have to do with GPS? So we had our system of equations before. Assuming that the clocks were not synchronized, we had the 4 satellites plus the fact that we know we're on the Earth's surface. And what we could get from all of that information was the Cartesian coordinates for our position. We got that x, y, and z. Where are we located? And so basically, what we need to do now, and this is again going to be the focus of most of today's lecture, how do we take that information and how do we get out a latitude and a longitude angle from that Cartesian coordinate? Okay? And so really the question then from a mathematical perspective is how do we convert between Cartesian coordinates and at least those 2 angular coordinates in the spherical coordinate system? The good news, as you might think, coordinate systems are completely interconvertible. They're just a way for describing locations and positions in space. You can choose any one you want so long as you're consistent. And if you have 2 that are consistently defined, you can always interconvert between the 2 of them. So that's the good news. What do you think the bad news is going to be? There's no bad news. There's better news. It requires a little bit of trigonometry. Okay? So that's what we're going to do. So this is a busy slide, but we'll talk about this more. So I grabbed the picture here from Wikipedia on what the spherical coordinates look like. And so notice now they've replaced that rho as now r, which is going to be consistent with what we see. And it turns out there's a nice system of equations that can be used to basically determine what are your spherical coordinates. Given x, y, and z, you can use these equations to determine r, what is your distance from the origin. Notice that r equals square root x squared plus y squared plus z squared looks an awful lot like our distance formula when one of the points is where? It's the origin. It's 0, 0, 0. So you can think about that as being x minus 0 squared plus y minus 0 squared plus z minus 0 squared. It's the exact same distance formula that we've been using the last couple of weeks. And then we have these two trig relations, the theta equals arctangent y over x, and phi equals inverse cosine z over r. We'll talk about these more, sort of where these came from. It's a neat little trig exercise to work these out. But I just want to add this word of caution here. Just be warned and remember that the inverse tangent function, so think back to your pre-calc a little bit, and maybe this is blowing off some really dust. There's some dust that was very happily settled there. Inverse tangent function will produce an angle between negative 90 and 90 degrees. Okay, so theta now is pictured here. Is theta our azimuthal angle or our polar angle? It's our azimuthal angle. So that needs to have a total range of what? 360 degrees. But inverse tangent only gives us something between negative 90 and 90. So how do we get that other 180 degrees? Okay? The answer is, and I'm just going to state the rule here, if you want to see more information, this link down here, the second Wikipedia, to this thing called ATAN2, gives a really nice discussion if you're curious, but I'll just state the rule. When x is negative, we need to modify the equation up there. That theta equals inverse tangent y over x is only strictly correct when x is non-negative. Well, strictly speaking, when x is positive. If x is 0, we're going to run into other problems. Okay? If x is negative, we need to add 180 degrees to whatever comes out of that inverse tangent when y is non-negative. And then conversely, we need to subtract 180 degrees when y is negative. Okay, so just we're going to put the rule there. Just keep that in the back of your mind when you're working. This has to do with the quadrant issue. Again, if you're thinking back to pre-calc, inverse tangent is only going to return something in quadrants 1 or 4 of the plane. If you're in quadrants 2 or 3, which was when x is negative, we just need to take what comes out and sort of shift it back over. And then the last formula, that phi is equal to inverse tangent z over r, works without any problems. And so that's how, given our Cartesian coordinates, we can compute these spherical coordinates. In particular, for the GPS application, we can compute theta, that azimuthal angle, and we can compute phi, our polar angle, and ultimately turn those into longitude and latitude, respectively. We'll come back to that point momentarily. What I want to do just real quick, because I know it's early in the morning and we all love good trigonometric exercises, is work through very briefly where those equations came from. I need to pull open a notebook. And so basically, what ends up happening is there's two key triangles that end up appearing here. So if we think about having our three-dimensional coordinate system, so here's maybe our x direction, we've got our y direction, and we've got our z direction. What we're going to end up doing, first of all, is saying, suppose here's our point, floating out in space. And to make this a little bit more concrete, we can draw a line from the origin up to that point. And then what we're also going to do is sort of draw the line from that point, projecting it back down into that xy plane. And so that's at a right angle right there. And as I said, there are going to be two triangles that really help us out. One is already pictured. We're going to get this triangle that's sketched out in the dashed black lines. The other one that's going to be useful is this triangle now that starts at the origin, goes to this point here on the x-axis, and up to this point in the xy plane. And here's why we're interested in those two triangles in particular. Assuming that we're going to use the positive x direction as our reference for our azimuthal angles, what is this angle that I've sketched out there in blue? Is that going to be our azimuthal angle, a polar angle, or none of the above? What do you think? That's going to be our azimuthal angle theta, because that's saying look in the plane, start from some reference direction that we're now calling the positive x direction, and figure out what is our angle from that as we sweep out in the plane. Okay, so that's just our angle theta. And then the other angle that we'll consider is either this one right here, which is alternatively the angle inside that triangle. I think, what is that, the interior angles theorem for someone that's taken geometry more recently than me? Okay. The point is those two angles are equivalent. And what angle is that? Is that a polar or an azimuthal angle, or none of the above? That's going to be our polar angle. In particular, that's that angle phi that we saw on the last slide. So what we can now do is work with these two triangles and derive those relations that we had on the last slide. So think about looking at this triangle in the plane. So we're going to come over here and we'll redraw it. So here's now our angle theta. So think about sort of if we rotate this triangle and sort of bring it back down. If theta was here in the center and it's now over here, there's our right angle. What is the length of this side right here? It's just going to be x. That's the distance that we had to go in the x direction to reach our point. And likewise, what's this vertical distance going to be? Now, which direction do we have to travel when we moved along this side of the triangle? That's just going to be y. Okay? And so what we can now do, well, so think back to our SOHCAHTOA. If we know something about the opposite side and the adjacent side, which trig function is going to help us there? That's tangent, SOHCAHTOA. So we know that tangent of theta is equal to the opposite over the adjacent. And notice then if we take the inverse tangent function, that gives us that theta equals inverse tangent y over x. That's all there was to it. Okay? Now, moving on for our other angle, what is the length of the hypotenuse of the right triangle that we're discussing? It's not quite going to be z. Because remember, this triangle is completely located in the xy plane. What's the length of this hypotenuse going to be? Yep. Okay, so it's going to be just the square root of x squared plus y squared, just using our Pythagorean identity. Okay? And so the reason why we need that is now we're going to consider the second triangle that we've got pictured or drawn here. So we're going to take this one that was in the dashed black lines that has our phi angle, and we can now draw that in some way here. So we know from the picture up in the top left corner, this angle here is phi. This bottom side, what is now the length of this going to be? That's going to be the same thing that we just found. That's the hypotenuse of the first triangle. Notice because they're the same thing here in the diagram, where we've got this now thickening black line there. So that's square root x squared plus y squared. And what is this vertical distance on this triangle? That's now going to be z, because that's now how far above that xy plane did we have to go to reach our actual point up there. And so what we can now see is that, so now we have, let's see, we have the opposite and the adjacent. Is it also pretty straightforward? What's the length of the hypotenuse of this triangle? This is now just the square root of x squared plus y squared plus z squared. But more specifically, that's now, using this distance formula, that's the distance between the origin and what? The actual location of our point. That is how far our point is from the origin. And in spherical coordinates, we give that the symbol r. That is one of our three primary coordinates. And so again, using a little bit of trig, we can use tangent again if we wanted, where we have our opposite and our adjacent, but it might be a little bit simpler here if we used the adjacent and the hypotenuse, just because r and z are simpler than square root of x squared plus y squared. And so in that case, if we're going to use our adjacent side and our hypotenuse, what we now end up getting is that the cosine of phi is equal to z over r. And again, if we apply that inverse cosine relationship, we get that phi is equal to inverse cosine z over r, which is exactly what we saw on the lecture slides. So I know that was a lot of really early morning trigonometry. I'm not going to apologize for it. But that's where those came from. So there's absolutely nothing mathemagical going on here. Okay. So let's come back to our notes and continue on. Or I guess, does anybody have any questions about this before we move back over to the notes and continue on? Okay. realistically, as we're working through the material in this class, you don't need to know those derivations, but I think it's just useful to show you where these come from. Again, there's no magic going on, and I want to show you where that is. But if you've got these equations down, hold on, click the wrong button here. There we go. Okay. But we've got these equations, and if you've got these and you just want to use them, that's going to be totally fine. Again, just keep in mind this word of caution about theta and dealing with the sine of x. Okay? So we can also go the other direction, and suppose we were given the spherical coordinates, we wanted to calculate our Cartesian coordinates. What's our x, y, and z value? We can go through an equally tedious trigonometric situation, basically working backwards of what we just did. We're not going to go through that. But if you want to take the time independently and trace it through, you're more than welcome to. And get that basically x is just equal to r times sine phi cosine theta, y is equal to r sine phi sine theta, and z is just equal to r cosine phi. Okay? So now, again, we can go both ways. Given x, y, and z, we can get r theta and phi. Given r theta and phi, we can go back to x, y, and z. The nice thing is these equations have no notes. They work all the time. Given r theta and phi, that's what you want to do. Okay? And so I think I've regrouped the equations here just for convenience, but let's take a moment to practice. And so if I give you the point x equals 3, y equals 4, and z equals 12 in spherical coordinates, or sorry, in Cartesian coordinates, what is that point in spherical coordinates? So maybe if you want to take a minute or two and work this out, and then we'll come back and discuss how we did that. Which one? The one that looks like a P almost. What, this value? Yeah. That's phi. And the other one is theta. Sometimes it's also pronounced phi, but there's no fee for learning except tuition, but that's not me. Good. I see people reaching for their calculators. Remember to put it in degree mode and not radians. Okay, so converting this over to spherical coordinates, we've got our three equations here on the right-hand side, or on the left-hand side, excuse me, because we were given our x, y, and z, and when we want our spherical coordinates, we want that r, theta, and phi. So we need to basically go through these equations. They don't necessarily have to be in the order that's presented, but I think that's the easiest way to go about doing it. And so we can start with our r equals, and we just need to substitute in our x, y, and z values that were given. And so 3 squared is what? 9. 4 squared is, and 12 squared is 144. And so when we add that all together, we end up getting 169. And what's the square root of 169? 13. Okay, so what that immediately is telling us is that we know our point is 13 units from the origin. Okay, and so let's write that up here just to clear some room to keep working down on the bottom. Okay, so then Theta is going to be inverse tangent of y over x. We can plug in our values, so we're going to get inverse tangent of 4/3. Now, is that right? Do we have to do any of this sort of funny correcting business here? Is x negative? Nope, so this formula is going to work just fine. Okay? And inverse tangent of 4/3, anybody's got a calculator? Do you have a number for that? 53.13. Yeah, it's about 53.1 degrees.
When we like do that on homework, like what comes up, like what do you want us to round up to?
Generally, so there's a question about rounding on the homework. Generally speaking, I would either give like 3 digits or maybe go to the tenths place on degrees. Yeah, 53.1 I think would be fine. Yeah, I think on any angles you get a tenths digit is fine. Okay, so what this is saying is, if we were to start, whatever our reference direction is in the plane, we're going to need to rotate 53.1 degrees to find the direction that we're at. Okay? And then the last coordinate that we need is to calculate our phi, or the polar coordinate, polar angle. And we can do that as phi equals to inverse tangent. Okay, z is now 12. We've already calculated r from earlier. We found that that was equal to 13. So inverse cosine of 12/13. And does anybody, again, have sort of a number from their calculator? It's about 22.6 degrees. And so what that's saying, again, to reach our point, we would start at our North Pole. We're going to come down an angle of about 22.6 degrees, and that's where we're located. Okay? So that wasn't that bad. At least I don't think so. Question?
So R being measured in degrees?
R, so is R an angle? So the question was, is R measured in degrees? Is R an angle? R is the distance that we're going to have from the center of the sphere, in our GPS example, from the center of the Earth to the surface. So would that be measured in degrees? Probably more like miles. Yep. So we said R equals 13 here because we didn't put units on here, but it would be like 13 miles, 13 kilometers, 13 light years, whatever the case you want. But R is a distance.
So is R like sort of a radius, kind of?
Yep. Sorry, the question was R like a radius? And the answer is yes. Okay. So that's one example, and we can go on to the next slide and see, sure enough, I think those values match up with what we had calculated. Okay, so now for the other example, doing a very similar thing, we can give the Cartesian point x equals -2, y equals 6, and z equals -3. And what does that look like in spherical coordinates? So the question I might ask you here is, why did I include this example in addition to the first one? Because, you notice, x is now negative. So there's a problem with something going on over here. What are we going to have to do? We're going to have to modify one of these formulas. Which one? The one for theta. Okay, so we saw earlier that when x is negative, we have to modify it. And the way it works is we then look at the sign of y. If y is negative, we subtract 180 degrees from what comes out of that inverse tangent. And if y is non-negative, we add 180 degrees. So in this case, y is positive, so we're going to need to add 180 degrees to whatever comes out of that inverse tangent. Okay? Yep?
So when y is positive, if x is negative when y is positive, you add 180. But if x is negative and y is also negative, you minus 180.
Correct. Yep, and that's spelled out, again, a few slides back in that little word of caution. Okay, so we can start working through this just like we did before. So we have our r is equal to square root. -2 squared is equal to 4. 6 squared is 36. And -3 squared is 9. When we put all that together, we're going to get the square root of 49, which happens to be 7. Okay, so we can make a note and save that for later. So r is equal to 7. Now we get to the fun one, where we're going to need to consider theta is equal to the inverse tangent of now y is 6 over x is -2. Could simplify that to be inverse tangent of minus, what would it be, -3? And with someone that has a calculator, that comes out to Yeah, it's like minus 71.6 degrees. Remember, we need to add that 180 in. And when we get done with that and put that all together, what we get is about 108.4 degrees, if I've done my math correctly. Okay? So again, what that's now saying, we started from our reference direction, but now to get to our point, we had to go rotate not only the full 90 degrees, make that about 90, but then actually go about another 18 degrees past there. So we've got this nice obtuse angle between our reference direction and our direction. Okay? And then lastly, we can go through phi exactly as we did before. I don't think we need to necessarily write that out. I'll just put up the answer here on the next slide, and we'll move on to another example. Okay. And so sure enough, there's our theta is equal to 108.4, and phi ends up coming out to be 115.4, which again says we start at our North Pole, we've got the full 90 degrees down to the equator, and we're actually a little bit below it. Okay? Which again, it signifies that z was negative. Okay? Any questions on that? All right. X and z were both negative in that example. Yep. Okay, so we can now go think about going the other way, take a spherical coordinate, and go to Cartesian. And let's take a moment and work one of these examples. So again, take a minute or two, try to work this one through, and then we'll discuss how it works. Okay, so which set of the equations are we going to use in this case? Are we using the ones on the left or the ones on the right? We're using the ones on the right, exactly, because we're now given the r, theta, and phi, and we're looking for x, y, and z. So we're going to use these. And were there any notes or words of caution on these equations? Nope, they work just fine. So we can plug in, for instance, x is equal to 4 times sine of 33.4 degrees times cosine minus 109.4 degrees. And when we calculate all of that out and convert it all through, what we end up getting is, at least by my calculation, about minus 0.731. Again, here, 3 digits, not necessarily after the decimal point, but just 3 digits, I think is appropriate. And we get that. And we can go through and do y and z in exactly the same way, just literally plugging in r, theta, and phi into those 3 equations. Okay? And what we end up getting when we're done with that calculation, sure enough, there's that x is equal to minus 0.731, y ends up coming out to be about minus 2.08, and z is 3.34. But again, pretty straightforward. Maybe a little bit of juice on the calculators to do this, but nothing tremendously complicated, I don't think. Okay, so let's tie this all back now. So we started this discussion by saying we need a way to get to latitude and longitude. And we stepped back and said, well, latitude and longitude are just polar and azimuthal angles, respectively, from spherical coordinates, or at least they're close to it. And so now what we want to do is tie this all back together. How do we actually go from these spherical angles to latitude and longitude? Okay, and there's a couple rules to follow. Let's start with longitude, because this one actually turns out to be easy. And what this ends up being is these are the conventions that we have decided. When we want to talk about latitude and longitude, this is how they are conventionally used. There's nothing special or unique about anything on this slide. This is just what we've adopted as sort of human civilization. Okay? And so what ends up happening is we already established that when it comes to longitude, our reference angle is going to, or our reference direction is going to be what? For longitude, what's our reference direction? It's the prime meridian. And so naturally, we're going to define that to be 0 degrees longitude. Okay? Correspondingly, the international date line, more or less, is essentially 180 degrees. Whether you go positive or negative doesn't necessarily matter. And so then what we're going to end up doing along these lines also, when it comes to relating the spherical and Cartesian coordinates, is we're going to say that the positive x direction is our prime meridian. So again, when we're thinking about that reference angle, when we did this a few slides ago, I said, let's assume the reference direction is that positive x. That is what is conventionally done. So when we think about putting our coordinate system on the planet Earth, positive x goes towards the prime meridian, negative x goes towards the international date line, somewhere over in the Pacific Ocean. Okay, so that's how we do longitude to some degree. And then likewise, if we want to think about where are the y-axes oriented, so the positive y-axis is going to go towards 90 degrees east longitude, and the negative y-axis is going to go towards 90 degrees west. So if we want to think about the longitude angle for something like New York City, we said ballpark New York City was about 70 degrees west earlier. What's that longitude angle, that theta angle, going to be for that negative 70 degrees, excuse me, for the 70 degrees west longitude? What do you think? How many degrees are we from the international date line? Or, excuse me, from the prime meridian? Wow. About 70 degrees. But by knowing that we're going west, it's going to have to be negative. Because we have to specify, well, we're 70 degrees from the international date line, but did we go 70 degrees west or 70 degrees east? And so negative values for theta are going to correspond to the western hemisphere, and positive values of theta are going to correspond to the eastern hemisphere. Okay? And so then the other way we're going to orient our axes, so thinking we've got our x-axis done, we've got our y-axis done, we need to consider our z-axis. And the way that we're going to do this is we're going to say our z-axis basically goes from the north to the south pole, all the way up. Positive z-axis is the north pole, negative z-axis is the south pole, such that when we're thinking about the polar angle, our angle phi, 0 degrees points straight north, 180 degrees points due south. Okay? And so then the way that this ends up working, when we want to convert these angles to latitude and longitude, longitude is really quite easy. Longitude is equal to basically theta. Take whatever that angle is. You're going to get rid of a minus sign if one exists, but noting that positive angles of theta, or positive values of theta, are east. So we would say, like, if it was theta was equal to 70 degrees, then that would tell us that's 70 degrees east longitude. If theta was negative 70 degrees, then when we convert it to longitude, we'd say that that's 70 degrees west longitude. Okay? But really straight conversion there. Theta basically is our longitude. And now what happens is latitude gets maybe just a slight bit more complicated, and there's no really good reason for this other than cartographers defined the reference angle for latitude to be what? It's the equator. Versus the mathematicians defined for our polar angle, the reference is going to be the North Pole. So we've got to convert between those two conventions. And what we can end up doing is just using this idea that latitude is equal to 90 degrees minus that polar angle, phi. So think about it. If phi is equal to 0 degrees, so this polar angle is 0 degrees, which direction are we looking at? Due north, because there's 0 degrees angle with that North Pole direction. And so this says our latitude would be 90 minus 0 is 90, and the North Pole is in fact 90 degrees north latitude. Okay, so similarly, as we keep coming down, so we can increase phi as we're coming down from this polar angle, and we eventually hit 90 degrees. Okay, that's the what? That's the equator. And so if we put in our phi is equal to 90 degrees, what does our latitude come out to be? 0. And is the equator 0 degrees latitude? Yep. And then lastly, for the check, we come all the way down to the South Pole. Phi is equal to what? 180. 90 minus 180 is negative 90, and we're going to play the same game, where now what will happen is, when we calculate out this latitude value, if it's positive, that's going to correspond to the northern hemisphere. If it's negative, that corresponds to the southern hemisphere. So at 180 for phi, we get that latitude value is equal to negative 90. The negative specifies southern hemisphere. We'll drop the negative for writing it, and we'll call that 90 degrees south, which is exactly where the South Pole resides. Okay? And so that's all that's going on here for latitude and longitude. And so I think we can work one example real quick. There's some other cool stuff at the back half of lecture. There's a couple examples, but I think we're going to skip through most of them. I'll let you work them out on your own time. But so we could ask now, what are the latitude and longitude coordinates for phi equals 51.1 degrees and theta equals minus 77? Okay, and the way that this would work, from before, on our last slide, we had latitude was equal to 90 degrees minus phi. So this is now going to be 90 degrees minus 51.1 degrees, which gives us, this is about 38.9, I get something around that? Okay, so that value is positive, which tells us we're in which hemisphere? Northern hemisphere. And so our latitude is going to be 38.9 degrees north. Okay? Longitude, as we recall, is even simpler. Longitude is basically just equal to theta. Now, is theta positive or negative? It's negative. So which hemisphere is that specifying? The western hemisphere. And so we convert that over. We drop the negative sign and call that 77.0 degrees west. Okay? Really simple to go back and forth between all of that. And I think when we put the answer up on the next slide, that should even match what we just did. Huzzah. And that turns out to be actually the latitude and longitude for Washington, D.C., if you were curious.
The longitude is, you said it's latitude minus something.
So the latitude is 90 degrees minus phi. Longitude is basically just theta. We don't have to do any corrections for theta. Just look at sort of the sign. Negative sign means western hemisphere. Positive sign means eastern hemisphere. Okay?
Theta was negative.
Theta was negative in this case, so that tells us it's a western hemisphere longitude. Yep. So we could go the other way around. We could try to calculate what are the spherical angles. If I gave you latitude and longitude, so now latitude's 33.9 degrees south, longitude's 151.2 degrees east. That happens to be Sydney, Australia. I'm just naming places I either like to visit or would like to visit.
So I guess you've been to DC.
I've been to D.C. many times. Haven't quite made it down under yet. Anyway, how can we go about calculating what are those spherical angles? And we basically just invert the procedure. So we knew that longitude was equal to theta. Okay, so now this theta is 33.9 degrees south. Sorry, that's phi. There's longitude. 151.2 degrees east. Is eastern hemisphere positive values of theta or negative values of theta? It's positive. So we know our value of theta is simply 151.2. That was pretty straightforward. And then latitude gets a little bit funnier. Just for brevity, I'll denote it as latitude, or as lat. It was 90 degrees minus phi. Well, now that we're given this latitude value, we need to actually solve this around, so we can say phi is equal to 90 degrees minus lat. Okay, so now what we need to do is convert this latitude angle back into sort of something that's positive or negative. So its southern hemisphere is that, it's negative. So what we're going to put in now is 90 degrees minus 33.9 degrees. So basically the minus of a minus is a plus. And I believe we get 123.9 degrees for that phi angle. And again, does that make sense? If we started at 0 90, 123.9. Does that put us somewhere in the southern hemisphere? Yep, good sanity check. Okay. And that's exactly what we got. Okay, so if you're curious, there's a website. You can go to latlong.net and look up latitude and longitude coordinates of locations. Google Maps can also do this for you in certain aspects. And so just to sort of summarize, let's sort of step back. So that's more or less the end of the GPS unit. Again, we've got a few other things. We've got some eye candy to fill out the last 10 minutes of lecture of some pretty cool stuff. But to sort of put this all down, the way the GPS works, when we start, so we pull out our receiver and we're going to start measuring data. What we're going to do is have to get the locations of the satellites, which is going to be tabulated somewhere. The Air Force is working really hard to make sure they are where the tables say they're going to be. And we're going to have to actually measure signal transit times. Those satellites are going to emit radio signals at certain intervals. We're going to receive them and figure out how long did it take those signals to reach us. Now, one of the things that we're going to have to do is that the locations of the satellite are probably going to be in spherical coordinates, which is to say we're going to know the altitude, how far above the Earth is the satellite, and we're going to specify it's at some latitude and longitude coordinate. So if we want to think about using that distance formula, we're going to have to convert all of that satellite information back to Cartesian coordinates to get some sort of x, y, and z coordinate for each satellite. Okay? Once we do that, we can calculate our distance from each satellite using that speed-distance-time relationship. We can then construct our system of equations using each satellite signal as one, and ultimately solve that to determine our location. That's that trilateration. Assuming the clocks are not perfect, how many satellites are we going to need? 4, and the last piece of information is we're on the Earth's surface. That gives us the 5 spheres we need. That's basically then doing trilateration to solve for our coordinates. And then when we're done with that, we will have our x, y, z position in Cartesian coordinates. We'll need to then convert that back over to latitude and longitude using the relationships that we discussed today in lecture. I know it was a long way to go. There's a lot of steps involved, but hopefully I've convinced you that none of them is independently that complicated. There's a lot of work to do, and this is certainly a tedious calculation. The good news is, are things like this really good at tedious calculations? Yeah, they are. Okay? And so that's basically how GPS is working. So what we can now do is actually look at a little bit of eye candy. And there's this really nice website here called inthesky.org. I've got some screenshots here that are from last February. But let's actually pull up a web browser, and we can come take a look at it. This is actually sort of a really cool thing. So you can come up here, and this gives quite a bit, but if you look and come to the spacecraft menu, you can see there's GPS satellite positions. I mean, this will basically show you a whole bunch of satellites, but we're specifically interested in GPS. And what it does, there's some, here you can see here's actually today, the time is about 9:42 right now. Let's just freeze the motion for the time being. But when we scroll down, we can look here, and when you see the map, it's centered, it's trying to detect our location on New York City right now. And we can see that there's a couple satellites. There's one actually not too far off the coast here. We've got one sort of crossing into Canada, one that's getting close to California, a couple over by Africa, some up over by Europe. But these are all different GPS satellites and sort of where they're at and showing more or less what's the trajectory right now. I think this website's also pretty neat because there are a couple different views that you can do. And the one that I like is sort of looking at these satellites above your position. And so what this is trying to say and show you is which ones are actually visible to you. So we looked at the last map, it's just showing here's the entire map. It wasn't the entire world, but where are the satellites. These are now the ones that are in principle. If we were to hold up our phone and look for GPS satellites, these are the ones we would actually see. Okay? And in particular, the ones that are closer to the center of this circle are the ones that are closest to us. So there's that one that wasn't too far off of New York's coast. These are probably the other ones that were sort of over, maybe in California, even starting to get close to Europe and all that. And you can see there are quite a few of them actually all the way out right on the horizon, sort of just at the limit of what we would be able to see. Notice now, can we see at least 4 satellites? Yep. So does that mean when we turn on our GPS receiver, we'll get enough information to determine our position? Yep. Is that by accident? No, it's not. Okay, and so there's a couple other different views. I would strongly encourage you at some point to go take a look at this. There's actually the 3D globe, where you can see sort of where the satellites are and how high up they're orbiting. You can rotate it around a little bit and sort of see what's going on. Anyway, there's a lot of really neat information there. Like I said, I would encourage you to go check it out. So I've just put that in. This website, unfortunately, they updated it about a year ago. It used to actually provide you with direct information where you could click on a satellite and learn its position at any point. So you would see, notice down here that it gives you, here's the latitude, longitude, and altitude of that satellite. I think this information is still there. They've changed the interface, and it's not as straightforward as just here's a tab on the thing that you could click and see. But again, I encourage you to go sort of take a look at the website and see what you can find. And so the last thing we're going to do in this unit, and certainly we will do this on Wednesday after we talk about the term paper stuff, is let's actually put an entire example together. So what I'm now going to say is, okay, so first of all, notice the last line here. The satellites and receiver are synchronized. So in that case where we don't have to worry about all the timing information, how many satellite signals do we need to see to determine our location? Just 3. Notice I gave you 3 satellites. Okay, so there's 3 satellites. I've given you their latitude, their longitude, and the transit time it took for a radio signal to reach us from that satellite. Some useful information. There's the speed of light. We will assume the Earth is just a perfect sphere with radius 4,000 miles. And let's also assume that satellites orbit the Earth at 12,500 miles altitude. It's usually around between 12,000 and 12,500. There's a little bit of variability. And so what I would encourage you to do is in the next 2 days, take a look at this. If you've got a chance to sit down and solve it, try it. If you don't necessarily have that much time, think about how would you go about solving it? What are the steps that you would need to do? I guarantee you have every tool at your disposal to address this problem. And what I'll say is, I'll give you a hint, this location, your location, is in the continental United States. The question that we'll want to answer is what city and state are you in, and I promise you it's a joke answer. So with that, I would be happy to take any questions. Otherwise, we are done for the day. Thanks for your attention, and have a wonderful afternoon. With the summary? Yep.